Alright, so I'm gonna load up a round, a 50 cal slap round for the Bluestone Militia here. How do you break a 10-year doctoral thesis with your 20K National Guard college fund? Do like, check this shit out. Should be fun.
Welcome back to recitation. In this video, I'd like us to find an antiderivative of the function 1 over x squared minus 8x plus 1.
8x, you say?
So I'll give you a while to work on it, and then I'll come back.
Find the integral of dx over x squared. Oh, well, how about Laplacian g metrics to the power n equal 8
so welcome
pi
back.
g
well, what we'd like to
t
do
metrics
is
to the power
find an
n t.
antiderivative
How about
to
that shit?
1 over
Field
x squared
theory.
minus 8x plus 1.
Complete,
and how we're going to do that is we're going to use the technique completing the square.
Do it.
And I'm going to set up the problem. I'm going to get it to a certain place, and then I'm going to let you finish it. And how do you know if you got the right answer? Well, you actually take a derivative of your answer and see if it gives you back 1 over x squared minus 8x plus 1. That's how you can check. So let's start off. If I want to complete the square, let's just remind ourselves how to complete the square on this.
Go on.
On this quadratic. So I'd like something.
So 2x2.
Right here.
I got the ball in water.
Square.
I got the ball in oil.
Right. Well,
8
the
pi.
8 here in the middle. If I want a perfect square,
so it's in the pipes. Here
I'm gonna have an x minus. I need a number here that when I multiply it by 2, that's where this 8 comes from.
And I'm going to describe what that axiom particle is at
right? Which puts what
spin
here?
measurement direction for
puts
potential
here, right?
probabilities of the wave function.
Just to double check, what I'm looking for is a number here.
You know,
give it more space,
right pop it out into the universe,
by 2 gives
and
me
then limit it to
and then I need it to figure out what it squares to.
in the direction
so that
to the
number's
first set,
-4
which is going to be
but obviously
eventually
this isn't
3
what I have.
dimensions.
Right,
X has got to equal.
So what have I had to do to get from here to
there.
here? Well, I had
then
plus 1, and now I have
really
plus 16, so obviously I've added 15.
Well, to figure out what frames
so I have
you
to
are.
subtract 15.
It's like, I don't remember, it's like Toonami, they had that AIs go where the little fairy touched him and blinked him out.
So
hey,
understand
don't
where
count
that comes
me.
from.
Blink, oh, I can see
Let me
physics
just
now.
remind you.
Kind of, but you got to get it there.
I'd like
You're
it to
probably
have
still doing it wrong.
A perfect
like
square,
the rest of us.
and then subtract a constant or add a constant.
All the time.
Right now I have
Constantly
something that
constants.
I don't have a perfect square in here. I can't make this into a perfect square unless I add a certain amount to the constant right here. So I had to add 15 to the constant here.
And or
Notice
if
16
and
minus
when
15 is 1. That's my check also.
if you
the lines are equal.
Bump into the wall.
So what I've done is I've added 15 and subtracted 15, and then I put this plus 16 into here. X minus 4 quantity squared is exactly these first 3 terms.
Good. Loading it up, Pinball Wizard, cling.
Now you might say,
why? Moving it forward, shifting the WIMP
so
through
let's make sure we understand
the neutrino
the square on
over into the G vector.
Back,
now, depending on how you doing math,
it's
how low it is. Is this one 2 to 1 on the particles of how they do? Because the WIMPs, all of those particles across the board.
Over
you know, the collision aspect, the velocity across once on the pipe, it's passing through superpositions.
Now you might say, Christine, this looks no easier.
Integral popping up through this wormhole over here, and some space-time numbers about.
Favorite or least favorite, depending on how you feel about it. Types of tricks we use now, which is the trig substitution. So some people love this because they just have to.
Go. Back into what I was just watching here. Well, we could have done that. Was that a new one? Oh, that was a new one. But anyways, you know, here in terms of the vector field where particles starts moving, and this might be base of my next page.
Every time I wear it, I get the best.
It's fair to say that black holes are the scariest objects in the universe.
Yeah.
Happily for us, the nearest is probably many light years away. Unless, of course, Planck relics are a thing, in which case they might be literally
and vector
everywhere.
Fields. It's like, and then they zero out. Always the zero, right? Only when
black
it's
holes are
relative,
scary
and
because
then
they're so
the vector fields
final.
of that force.
They're surrounded by this surface that we call the event horizon, whose defining property is
and
that nothing
arrow,
that falls beneath it can ever
it's
emerge. And if nothing can emerge from a black hole, then black holes
field,
must be
A,
neutral, black, they can't emit light,
or
and B, eternal. They can only grow in size, never shrink. At least that's the black hole as it appears in the mathematics of Einstein's general theory of relativity. But general relativity is not the whole picture. Back in 1974, a young genius named Stephen Hawking showed that if you bring quantum mechanics into the equation, quite literally, then the black hole is neither black nor eternal. He showed that black holes must radiate and so slowly leak away their mass in what we now call Hawking radiation. In a way, quantum mechanics saves us
The
from the eternal
particle,
black
this
hole.
guy, like
Except perhaps that it doesn't.
Kyle on
If you calculate
probability
the
or
evaporation
dimensional
of the black hole
analysis,
all the
you
way to the
can't
very
throw
last
all
instant,
the numbers away.
Quantum mechanics
They
may well play a
add
second
together
trick and
in
save
their
that
own
final
field
speck
theory,
of
but the
the
way they
black
collapse
hole
to zero
with
when
the
it's only
smallest
relative in the
conceivable
field.
size. These remnant black holes, or
Right.
Planck relics,
and then
may be everywhere. To
LP
understand Planck relics,
to
we
minute
need a quick
physics about
review
the
of
atom
Hawking
there,
radiation. Now, this is
and,
something we covered in
you
gory
know,
detail previously.
why
So for now, just the parts that we need
lambda,
for today. Hawking's
Cal-
discovery of this black hole
Hawking,
radiation was
they're
really
when in
ingenious.
that field, bing,
It came
you
from
know it's gonna
thinking
go
about how black holes interact
positive
with
or
quantum
negative.
fields from which all elementary particles arise. Now, to do this properly, you really need a theory of quantum gravity, which we don't even have now and certainly didn't in 1974. But Hawking used
It
a sort
would.
of hack, a brilliant
That's a little
workaround
number
to
on
prove that
dark
if an
body or
event
black
horizon
body
forms in
radiation
a
spike
vacuum,
up on you when you're about
then
to go
the vacuum
supernova.
states
You
of the quantum fields have to be
Fermi,
disrupted.
you little.
To a distant observer, it would look like the black hole is radiating particles.
Had enough of your
Hawking
Fibonacci
even figured
sequence,
out
Larry.
what that radiation should look like. It should be thermal. The distribution of particle energies should follow
One
a black
particle hitting
body
the wall,
spectrum,
and then
as though the black hole had a real
that's
temperature.
acceptable, but
In the
it's
common pop
not
sci
when
description
it's
of Hawking
on
radiation,
the
you
other
often
end
hear
of that.
about particle
Too much
antiparticle
spinning
pairs
on this
appearing
thing
at the
for the
event
black
horizon.
hole
One gets
to
trapped,
make it
allowing
work
the other to
functionally.
escape. This is misleading.
You know, I need
For
some
one
way to
thing, the
stabilize
radiation doesn't
north, what's
appear
right
right
hand
above the
roll,
event horizon.
what's
Instead, the
condensed
wavelength
in
of the emitted
this
particles
observation
are
kind
about
of
the
plays with your
size of
face
the whole
equation
event
a little
horizon.
bit, because like I
So
said,
they sort
electrons
of
coming in
emerge
to
from the
feed
entire region
Fermi
surrounding the
land,
black
right?
hole. For the black
And
hole
Fermi-
left behind when a massive star
The rabbit-
dies, the event horizon is
the
several
result
kilometers
Higgs
in radius. For
and
such black holes,
antimatter, dark
the Hawking
matter,
radiation
news,
is
whatever,
just
whatever they're
photons,
getting.
electromagnetic
Kind of
waves with
normal, 8
kilometers
black
long
holes a week
wavelengths.
over it
So
at Lego,
really, really
right?
low
You know, and
energy
they
radio waves. Such a black
Like
hole
the
would appear very cold and would leak away
rings
its energy very
Saturn's
slowly.
magnetic
But as the
field,
black hole shrinks in
mathematics,
mass
to
and
ball
in
in air,
size,
ball in
its
water,
Hawking
to
radiation also
astrophysics,
decreases in
walk around this
wavelength,
thing.
but it increases in energy. That means the black hole appears to heat up, and the evaporation rate increases.
And
This
goes,
leads to a runaway process, and so the final stage of the evaporation should be positively explosive. That gives us a nice picture of a far, far distant future in which the stars have all gone, and we only have black holes which one by one vanish in bright pops of Hawking radiation. These days, most physicists agree that Hawking radiation is a thing. Researchers have come up with different hacks
Kind of
for
like
combining general relativity
WIMPs could
and
be a
quantum
good
mechanics,
candidate
and they
for a
reach the same
thing.
conclusion.
Einstein's field
But
theory
these are
is
still
we'll figure
hacks,
it out. We'll make
approximations
stuff work.
that involve different assumptions, or only work in certain ideal circumstances. One big assumption is that the space near the event horizon isn't too strongly curved compared to the smallest quantum scale. When Hawking made that assumption,
Yeah.
it enabled him
This
to
is,
mathematically
again, he's
connect the
making
high gravity region near the
Weevil's
black hole
accountants
with a very
numbers in the
distant
math
zero
house
gravity
about,
region where
well,
the
they're all
Hawking
looking at that and
radiation is observed.
they missed
Now,
one of these
that's
on there.
reasonable for most
about,
sizes of black hole. But
the
Hawking's
one that are like
entire
those
calculation falls
pesky
apart when the
facts you
black
bring
hole
to the
has shrunk
table
to the
on
tiniest quantum scale.
observation.
At that point, you need a proper theory of quantum gravity to describe the process. Without that theory, we have no way to describe the final stage of black hole evaporation.
It's tough.
So, it's reasonable to
The,
ask,
the whole thing in
does that
action,
final
like I said,
pop
Fermilab.
really happen? Think about it this way.
This-
a red-hot poker
this thing
glows
happens.
because it has an enormous number of iron atoms vibrating with every possible energy. In that motion, they produce thermal radiation that includes
How many
every
times did you
possible
mess it
wavelength
up?
of light. But if you zoom in on a single iron atom, it can't emit
By
every
math.
wavelength of light. It
That's how
jiggles in
fast.
this little crystal
I know,
lattice cage
it was
with very
that
specific
fast.
vibrational modes, producing photons of specific energies. So, a
Catch you
large
on the
black
next one.
hole is like our